Hello! So let's talk about space stations, specifically how to simulate large rotating space stations with open source software. This is a very obscure niche of video game development, but fortunately, open source software is perfect for obscure niches, so let's see what we can do with that. First, let's talk about what we're actually talking about. For instance, this is the Stanford Torus, designed by a group at Stanford for a NASA study in the 1970s. It was designed to support about 4,000 people, is 1,600 meters wide, and the tubes are about 130 meters wide. People live inside the tubes so that when it spins around, there's gravity, or something that feels like gravity, along the edges. It's like if you were holding a bucket with a string on it and then spin it around and around. The water stays in the bucket because of centrifugal force. It's not force like Earth, but it's like enough to keep things sticking to the sides. In the world of hard sci-fi, where you try to stick to basically known science, your options are for gravity in space are basically spin gravity, and that's it. Otherwise, you have like fantasy gravity, like Star Wars, and Star Trek, and that stuff. Doing this in reality, producing gravity by spinning things, has only been done a few times. There was one experiment with the Gemini 11 mission in 1966, where the capsule was tethered to the so-called Agena vehicle, which was this vehicle that went up with the rocket to simulate, to test docking procedures. So they took the Gemini capsule, tethered it to this thing, and made it spin just slightly. It only produced 0.00015 Gs. It was only like a proof of concept, so not like practical gravity or anything. They were trying to see how stable tethered systems could be. They weren't really going to test the full range of gravity. Other than that, there's been no real studies of how people behave in spin gravity environments. We've got lots of data for how people behave in 1G on planet Earth, and a little bit of data from the very few number of people that have been in space in 0G, but there's like no data for in-between G amounts. So like moon gravity, Mars gravity, if people live there for long periods of time, we have no idea what effects that will have on people's bodies. So in light of that, various groups have come up with these different scenarios for like the Stanford Torus or the O'Neill cylinder for how to make space stations that produce basically livable gravity about 1G typically. A lot of the designs that people have made through the years totally discount the severity of radiation in space, because at the time, in the 70s particularly, these things weren't really known. For instance, if you're floating in free space away from Earth's magnetic field, you could only be there for like half an hour before you get the maximum recommended daily dose of radiation. On Mars, it would be kind of half that, because you're sitting on the planet and the planet is blocking so much space radiation. Mars' atmosphere doesn't block very much radiation. But anyway, that's a deficiency of realistic designs. If we turn to fiction, there's all kinds of examples of spin gravity in fiction. The most famous probably being in 2001, the movie, The Space Odyssey. That has not one, but two different spin gravity configurations. One big space station, Station 5, and then the Discovery ship that the guy runs around in. There's the famous scene, the guy is jogging around in the rotational environment. To film that, they built this big set that rotated so the guy could run, and the whole set rotates around him. Many ways to fake things, like with computers these days, but then they did it practically. There's lots of other fictional rotating space stations, like in the book Rendezvous with Rama, in TV shows like Babylon 5, movies like Elysium. The Martian has a ship with a rotating environment. A recent movie called Stowaway has a tethered version of rotating gravity. Pretty rare to see that in movies. There's also the Expanse TV show. There's numerous examples of spin gravity. They do very good with the science. In video games, it's much more rare to have actual rotational physics. The closest you can kind of get is a game called Vanquish. That's only like for scenery. There's like a big round environment that you have to traverse through at one point. But they kind of gloss over the physics aspect of it. It's just scenery. Mass Effect has something called the Citadel, but that's not really rotational physics, rotational gravity either. It just looks vaguely like an O'Neill cylinder, but the gravity there is like magic space gravity. It's not actual physical reality gravity or spin gravity. Anyway, so getting back to software, VR is the best way to explore these things and get a feel for how these things actually function if you were there. If you're just looking at a flat 2D screen, it's very difficult to really understand how things move around, or like what happens if you toss something across the room. How does it behave? VR, however, is great because it blocks your whole view. You can control everything you're looking at. It's so immersive. You can pick stuff up, throw things around, and see how they spin around and whatnot. It's a great medium to explore strange physics environments like rotating space stations. A few years ago, when I was just starting on this journey to simulate space stations for some reason, I made this 2D version, but it does okay with showing how things move. Spin gravity is not true gravity, so when you throw something in this rotational environment, it actually goes in a straight line. Since you're rotating along with the station, it doesn't look to you like it's in a straight line. It like goes around, like as you can see here. It's things just like they go in strange curves. If you throw one way, it changes kind of directions. It changes speed compared to when you throw the other way. There's lots of little peculiarities. And 2D versions like this do okay at showing what's what, but it's nothing like being there in 3D with full immersion. One thing about this 2D simulation is you can kind of see where when you throw something straight up, it's like moves to the side. If you were in an elevator going up, for instance, you would behave exactly like that ball. So if you were going up in an elevator in one of these things, you'd be kind of pressed to one side. And if you're going down in an elevator, you'd sort of be pushed in the opposite direction. So in terms of designing stations, these gravitational things, you've got to be able to simulate or like give safety instructions for how to counteract those things, particularly like climbing up ladders for Jeffries tubes or whatever. In VR, of course, you don't have the full physical effects on people wearing the headset. You only control the vision. So people aren't going to experience the being pushed to one side or the other as they go up and down elevators. So in a way, that's good. So in VR, you get most of the realism, but only half the nausea. Okay, so that's what we're talking about. Now let's get into the how. I've been using Linux to make artwork for a long time, and the last few years I've been getting into video game development. I prefer to use Linux all the time. Sometimes I don't really have a choice, like with contract work or whatnot. They want to use Unity or Unreal, and those work best in things that are not Linux. But I'm trying to stick to Linux as much as possible. I've used Unity a lot. Unity can run in Linux. It's a little spotty in places. VR support in Linux is not really there. Unreal can sort of work in Linux. Whenever I try I can get it to compile, for instance, but often it'll have these mysterious hangs, and it's a little glitchy. Fortunately, there's also Godot, and Godot is cross-platform, runs in Linux. Great. It even runs in VR. You can build for VR pretty good. Also, Godot is extremely small compared to like Unreal or Unity. The executable size is like 70 megabytes. It's super tiny, whereas Unity and Unreal is many, many gigs. Also, Godot development is rapidly increasing month by month. It seems like they have some fancy new feature that they're introducing very often. I wouldn't say Godot is glitch-free with VR or in general, but I have every faith that over time these things will be worked out. It's a pretty small team. It's all open source. You don't have to pay royalties for using it, which is fabulous. Things get fixed. The development team is very responsive. So on the whole, Godot is a great choice, I think, for small developers in particular. It's pretty easy to use, and you can do VR. Of course, the problem with VR is that it's very expensive. My Vive originally cost $800, a long time ago. You can get a Quest for much cheaper, the Oculus Quest, but then you have to deal with Facebook, and some people don't really want to do that. I'm sticking with my Vive for now. Anyway. So let's get into Godot a little bit. Here's one of my earlier prototypes, just to demonstrate the basics of the rotational system. Here it's a kind of a dumbbell system. It's not with ropes, but with a truss, as you can see. There's engines on top and engines on the bottom, and it's just like you can press these interactive controls down here to make things start or turn around when it's actually running. Plus there's a monolith here for easier transport. I mean, who doesn't want to fly around on a monolith? So also a background using Jupyter as a backlight, because otherwise it's like really dark. With this early prototype, one thing I noticed right away is that when you're standing on this thing riding around, the entire star field rotates. When you're in that actual environment and you see all the stars rotating, it's really disorienting. If you're prone to nausea, that's a real problem. So if people actually make these rotating space stations in the future, people are going to be throwing up like all the time. So that's one thing I've learned from this. I personally don't get nauseous in these things, so that's lucky for me, I guess. It's still fun to make these things. You can make the rotation speed less to reduce that, or like have other fixed things by putting walls with opaque windows, for instance, so you get the physics but not the exterior rotation of things. There's ways to mitigate the nausea factor, is what I'm trying to say here. So anyway, in Godot, there is a bunch of different elements that I was combining in this early prototype. One is a VR rig that's based loosely on Bastian Olich's work. He was recently hired full-time by Godot to work on VR integration, which is great. So I'm looking forward to great things happening there. One thing that I had to convert a lot from his demo projects was, for instance, this teleporter. You couldn't really teleport naturally in a rotating system because when you have the whole system rotating, the teleport arrow doesn't really go where you want it to go. One time it's in one instant it's in one place, and then you rotate, and then it's a completely different orientation, except the underlying code expects things to be straight up and down. So that required a lot of refactoring to get teleportation and basic locomotion in VR to work. Another deficiency with these big rotating systems is that in VR and game development, there are these things called colliders. So if you throw something around, there needs to be a collider defined so that things know not to go through other things. But when you have a large rotating system, these things get munched up because a collider expects to be in a certain position. Then if you just arbitrarily rotate it to a new position, the collider information is kind of lags behind. So sometimes you teleport and the target for your teleport doesn't keep up with the rate of rotation, or you throw something and the colliders are not quite where they expect it to be. So I've had to do some workarounds for that. One way is to arbitrarily define a cylindrical surface as a fake collider, so you don't have to provide a gigantic collider, just detect it specially. That's a little unreliable because certain physics interactions have a lot of strange rotations and like bouncing off things that end up destroying your physics simulation. One way to combat that is to have the actual station stationary but rotate the background. For instance, I built this basketball court, so it has very solid walls, except there's just a little bit of a sliver, so you can see that you're in a rotating environment, but you don't get the full nausea-inducing rotating field effect. I think it works pretty well. You still get the strange rotational effects on the objects that you throw around, but you don't get sick from your whole world rotating around you. This station was also, I made this one after the previous dumbbell one to kind of work out physics interactions and ways to do colliders and stuff like that. So I made, as you can see, different types of basketballs, very loosely defined basketballs to toss around. This gravity, you can clearly see that's if you throw balls in one direction, they behave one way. If you throw them in the reverse direction, 180 degrees behind, they go in a completely different speed. So if you were to actually play this basketball in reality, it would be very difficult to synchronize things, because things are not going to behave the way you really want them to. Basketball really expects to have more gravity to it. It'd be a completely different game. Still worth playing, probably. It would still be fun, but it's a completely different experience. Here's a variation of the basketball court. This one has 3 basketball courts instead of just 2. And in this one, it's way easier to actually make baskets. It's still kind of hard to make baskets because the balls take strange trajectories because of the Coriolis effects. For instance, there's the ball shooter. You can see kind of how things behave. They make this weird arc going through the sky. But still, it's compared to the 2-chord version with the alternate 90 degrees difference, it's much easier to play. So before moving on to other rotational environments, let's talk a little bit about some more basic VR nuts and bolts. For instance, movement. In VR, to move around, players usually have the option of teleporting or continuous movement. A lot of people have nausea with VR, especially when they first come to it. So oftentimes teleportation is kind of a safer way to move around. That's where you take your wand or whatever and you point it at a particular spot, and then you instantly teleport to that other spot. That way there's less going on that your brain can interpret as wrong. So usually the nausea results from your ears. The sensors in your ears are telling you one thing, but your brain is telling you something else. When those 2 scenarios don't coincide, then your brain says, oh, what's to hell with you, this is messed up, and it makes you sick to try to get you to stop you doing what you're doing. So there's tricks like teleportation or like blacking out the surrounding areas from your field of view, so there's less to confuse your brain that something is going on that shouldn't be going on. So that's teleportation, and the other way is continuous movement. So for instance, in this video, this is showing the continuous movement only with climbing. Climbing is a little bit more complicated than just simply moving around, because in VR you don't just have a character, you have a whole little play area. So let's say their VR origin is here, your camera might be over here somewhere. So if you're moving around, you can't just move your character, or you can't just move your camera, you have to move your entire VR play space. So if you're climbing and going up and down, when you pull, your controller might be going down, but you have to synchronize your VR origin to kind of keep up with the movements that your controllers are doing. Or if you're spinning around, for instance, with continuous motion, if you're here and you move your camera around like that, and your origin is here, you have to do some math and figure out where that new origin is supposed to be so that you keep the internal VR state all synchronized. Another thing about climbing in VR is that you have to watch out for other hazards like dinosaurs. Technically technically or pteranodons, I think, were vegetarian, so they're probably not going to eat you, but they do have a lot of mass, and you got to watch out for stuff like that. One other thing about movement is that some games like Beat Saber and Pistol Whip, they have continuous motion, but fewer people have nausea with it. This might be because the movement in it is like as if you were traveling down some tracks. The movement is constant. And when there's constant activity, like repetitive, the same thing again and again, the brain is much easier at being able to filter that stuff out, as opposed to something that's like moving in all kinds of different random ways. Here we see a COVID-based Beat Saber clone that I made to demonstrate this constant motion. It also depicts my country's previous president's COVID response, which leaves a little bit to be desired.
Aside from movement, we also need interactable controls. This video shows one tool that allows you to make random shapes, in this case things that are almost low-poly pumpkins. This is based loosely on similar convex hole tools in TiltBrush and Modbox. Internally, this was an exercise to learn how to create low-level plugins for Godot, which has something called GD native, which makes it somewhat easy to extend functionality with low-level C++ code without having to recompile the engine itself. This is useful if you have like some library you want to pull in and use for some reason. In this case, it's using libqhole, which is not an easy library to work with, I have to say. But once you get it to more or less function, you can plug it into the GD native framework and then have access to it. Then once you have it compiled and installed into the Godot add-ons, then you can make something like this to, for instance, to capture points from a VR controller, then send it through qhole, which creates a convex hole, take that and then convert it back into a new geometric shape. Potentially, this tool could be used to fill out scenery with things that are half procedural and half made by humans. In addition to exotic interactions like convex hole, I also put together a bunch of more mundane things like buttons and levers for VR interaction. For instance, here's an example of using some of those buttons in a keyboard. This also provides a different type of Godot plugin that lets you change things dynamically in the editor. So in this case, you can change the curvature of the keyboard. It kind of wraps around a torus. This is all based on scripts that run in the Godot editor, so you don't have to compile anything. It's like mid-level between not writing code and then writing the GD native. It's using what they call GD script, which is very Python-like. So if you know Python, you're going to be able to do GD script pretty easily. It's not a one-to-one correspondence with Python, but there's enough similarity that's you can. Python will take you pretty far with GD script. And here's that keyboard in action in an actual VR environment, in this case a library. So you can either use the pointer on the VR controller or press down and it does collider interactions to figure out if you're pressing down on something. It sends the keyboard input to something else that processes it. That pulls the book from its shelf. You can look up other strange books in this library, sort of. You might have to go to other places to access the book. For instance, go around the edge here. Here we see some shaders and actions and a different type of keyboard. This keyboard runs off of JSON configuration files, so you can set up either English, French, whatever other keyboards. Just have a JSON file for each different scenario you want, and you can just with like a single import, automatically create a new keyboard to use in the VR environment. And I've made this keyboard available in a GitLab repo. It doesn't have to be VR. It can also respond to mouse clicks pretty easily. This library, by the way, demonstrates an interesting problem for optimization. So what I mean by that is this library consists of a whole lot of repeating objects, or at least a few objects that are repeated tons of times. However, this is modeled in Blender, and then when you model things in Blender with an array modifier, which is just taking something and repeating it a bunch of times, when you export it, it takes all of those things and combines them into the same mesh. So when you're in the game engine and you're trying to render something, if you're looking this direction, say, and then you run the game, it renders not only what's in front of you, but it has to figure out all of the rendering information for all these other corridors, even though you're not actually looking at it, because they're included in the same mesh. That's a problem with the Blender array modifier, because it does create a single mesh out of the copies. Sometimes you want that because the array modifier can merge things along borders, and sometimes that makes a very clean mesh, and sometimes that's what you want. But in terms of like game development scenes like this, it's not really the best thing in the world. So there's a few ways around that. One way is to use a particle system and then have objects spawn on those particle instances. Then when you go to export, each object will be its own mesh. So then when Godot tries to render things, if something's behind, it'll get cold before it's rendered. Another way to do it is keep the array modifier because they're easy to work with, but then make a converter script that reads the array modifiers and then converts them into their own instances. So like here we have a cube with two different array modifiers, an object array or an object offset thing, plus another more conventional array duplicator. So if you run that script in Blender now, it takes the original object and each instance of the array becomes its own object. It doesn't do any fancy merging or anything. It assumes that you want to have the separate objects, which in the case of this Godot project is, in fact, exactly what I want. So when you do that, all these objects that are behind don't have to be rendered necessarily, so they get culled out. That can lead to drastic performance improvements when you go to actually run the game. When you're trying to do things in VR, optimization is very important because you have to, you're basically rendering your entire scene twice, once for each eye. So any little tricks you can do to get performance frames out of it, then definitely that's something you're going to want to do. Now, on the subject of building repetitive things out, you can do tricks with the Blender array modifier if you want. But if you're already targeting VR, you can instead make tools that let you build things directly in VR, which in my opinion is way more entertaining. So for instance, here's a tool that I made based on the Mosque Cathedral in Cordoba. You might recognize those arches if you've ever been there. But here's the tool operating in VR. There is a few components. The arch is one component, or the top arch is one component, and the columns are another component. In VR, you're just grabbing the edges here and then dragging them to either side. And in doing so, the internal code adapts to how you're doing it and fills in as many columns as you need to create big arrays of stuff. This is using Godot's Multimesh Instance capability, where it's taking one mesh and then repeating it a bunch of times, but it's essentially acting like the same mesh. It's much more efficient to do it that way than have 100 different things all rendering at different times. So now let's return to rotational environments. One complication with big round space stations is that you can see the entire map all at once. And this means that Godot will try to render everything all at the same time. In normal game environments, that's not really true. You only see a portion of the map that's right next to you. You might see some buildings that are way off in the distance, but normally it's only the stuff that's right near you. But we can't do that. We have to see everything all at once. So we've got to use every trick in the book to try to optimize things down to get some extra frame rates. If our environment uses a whole bunch of repeating things, we can still utilize the Multimesh Instance to great effect. Godot's Multimesh Instance takes a single mesh, but then you can pass in, you can write a custom shader to accept individual parameters per instance. So like say you have 5 points, each of those 5 points has a different value associated with it. You can write a shader that takes those individual points and then does something random with it, or something according to a gradient value or something like that. It's an easy way to do a lot of variety of things, and people will think you're doing more than you're actually doing. It's a great way to go. And also, each mesh can have different materials. So if you make a mesh with like 3 different materials, it's basically the same thing as 3 different meshes, but you can still use it in the single multi-mesh instance of Godot, so you can get away with doing lots of different stuff. This video shows this in action. It's taking a single hexagonal crystal and responds to various interactable triggers in VR. Each of the VR triggers causes different parameters to be sent to the shader, and the shader then distorts the mesh. In this case, it's changing the thickness of the crystal and the size, and it's keeping the cap the same dimensions, so it's not scaling it uniformly. The cap is dealt with differently than the width of the crystal, and it's also adding some extra tilt to each crystal individually. Now let's take a look at another instance of using the Multimesh Instance and a shader. So this uses the regular repetition, grid-like repetition, plus it uses a shader to bend things into place. So here you see my C-wheel steering device boating around a thing inside of a rotating space station. You can't really tell that it's rotating in this one. It's more just a curved surface. But it's using a single element, and it's repeating a whole bunch of times. I can't remember the exact number. It's like 15 wide by like 100 around. I was getting about 70 FPS, if I remember right. So it renders pretty quickly without doing particularly any optimization. There's no colliders here, though, either. So I was very careful to steer around these meshes so that it didn't seem like I was going through them. Meshes are step 2. I mean, colliders are step 2. Here's the mesh that's actually being used, the single unit. It's rectangularly made in Blender. It has 2 materials. That could be reduced to 1 material probably, but the blue is emitting a little bit and the gray is not emitting, so maybe I can't do it in a single... I could do it in a single shader. That would reduce the draw calls, but right now it's 2 materials and a single mesh in a rectangular grid. And then the shader is taking that and then warping in the edges so that that rectangular object fits around a circular array. It's repeating once in one direction, and then another time it's repeating in one direction and then repeating in the other direction. And as you can see, there's like hundreds and hundreds of these things, and it still renders pretty quickly. If this were not using the shader to bend things around, it would overlap too much on the top because the bottom would be bigger than the top. To fit in this cylindrical environment, it's got to be like squished in at the top, which the shader does. There's a little bit of fog in there, plus a light. That's the actual boat you're driving on. The boat needs some rendering work. Fancy little light to draw on unsuspecting space travelers for fishing purposes or something. I don't know. So next we move on to another example of taking a rectangular component built in Blender and then squishing it around the edges so that it fits inside of the cylinder. This one uses a few different chunks arranged to fit together instead of just a single mesh. This station also serves as kind of a testing ground for traversing. So here we see just walking along paths and avoiding the water. I really need to put in a water shader or something. It's like shader fish swimming around. So right now the blue just isn't cutting it. Anyway, so in this station there's colliders interspersed around the stairs. Those big columns in the middle are eventually going to be trees with overhanging branches and vegetation. So many things to do. This one is a very unfinished one. I still have to implement opening the doors for the little hobbit houses. Right now they're just doors, you can't actually go in them. This station was also a test bed for interactable things inside of an environment that wasn't a perfect sphere. So like with these balls, you can toss them around and then they hit. There's a bigger variety of colliders for things to bounce off of compared to the basketball station. I was really trying to see how performance would change when you have a whole bunch of different collider instances. I still need a lot of research to do. Oh, there's also a space baby, the star child. It gets into a little bit of trouble. I put the baby in there just to experiment with character rigging. It's a model that I got off of BlendSwap and then put in a rig, combining it with some interactable baby bouncer there. Oh, there's another dinosaur, another space dinosaur you got to watch out for, and the return of the monolith. So this is the traversal I was talking about, to have vehicles that allow you to traverse these big space stations relatively easily. Still need to work on rigging. Rigging in VR is a lot more fun than rigging in Blender or anything else. Unfortunately, there are very few tools that let you rig things in VR. I'm slowly working on that. I don't really have a functional prototype for that yet, just some plans. All the stations I've shown so far are really just practice leading up to this next station, which is substantially bigger and hopefully better, eventually, anyway. In discussions about space habitats, there's a lot of talk about where to put stations. Because of radiation in space from the sun and galactic cosmic rays, it's very important to build somewhere either that has a lot of natural radiation shielding, like asteroids, or you have to build in a pretty thick, like 10 meters thick, shielding of lunar regolith or some other material, water perhaps. The only alternative to that would be to position a station in equatorial low Earth orbit. That way the Earth's magnetic field is still protecting you, but you're not like hanging out in the Van Allen belts and get roasted by radiation. So if you don't want to orbit in low Earth orbit, James Logan and Daniel Adamo has proposed to place a space station inside of Mars's moon Deimos. Mars has two moons, Phobos and Deimos. Phobos is closer to Mars, but they say that Deimos would be better as people can beam directly to a higher percentage of Mars's land area. Since it's further away, you're able to see more of the surface of Mars directly. Plus, since Deimos is further away from Mars than Phobos, to land there you would not have to fight as much against Mars's gravity well. The moons themselves have almost no gravity, so once you're in basically synchronous orbit, you would just have to kind of pull up to it. There's not a lot of... You don't have to thrust against very much once you're at one of the moons. Also, both moons are tidally locked to Mars, so that if this is Mars, each moon is going to face the same direction at Mars as it's orbiting around. Another quirk about the moons are that Phobos orbits in the opposite direction as Deimos, and it has a much shorter orbital time. So, if you're standing on the surface of Mars, Phobos is going to rise in the west and set in the east, and Deimos is going to be the opposite. The orbit of Deimos is approximately 30 hours, I think. I'll have to look that up, don't quote me on that. But it's more similar to a day, and Phobos is 1/4 of that or so, the orbital time. So, the largest rotating space station that I've been working on is to simulate in VR. The idea would be, what if you drilled a big hole in Deimos and stuck in a rotating station? I've been building it so that it's pointing, one end is sticking out of Deimos, pointing at Mars, so you would at least get one pretty good view of Mars while simultaneously being shielded from most of the radiation that you would see from open space. So here's kind of the view walking into what I'm calling the Deimos veranda. So you go through those twisty corridors and end up at this big platform, almost like it was Mass Effect, except it's instead of the sun out there, you see Mars. You have some benches to sit in, some space age lighting, lots of doors. That's a lot of airlocks. If something were to crash through a window, that would be a lot of doors to shut. Probably don't need that many doors. But anyway, so you go back out through these corridors and then go into the main chamber of the Deimos station. So there it is, under construction. This station would be about 1 kilometer wide and rotate such that you would have 1G. So let's take a look at how that is constructed, the Deimos veranda. Here's a piece that's exported from Blender. It's a really long corridor to have an air shaft. Down below, there's the twisty corridors, 3 on one side. I made these bent so that kind of a dual purpose. It blocks some extra radiation that would be coming in through the windows. Plus, since you can't really see through them all the way, they can act as a rendering blockout. So once you go through the corridor to the inside, you don't have to show everything that's inside when you're outside or on the other side of the corridors. So it's a little hack to improve rendering speeds to have these twisty corridors. So that's one chunk, and then that chunk is repeated all the way around that whole veranda. And so one thing that's pops up in this, since this station is so large, an actual 1 kilometer across, oftentimes you get clipping issues. So for this, I always have to set this way up just to get everything so that I can see everything down there. When you change the clipping distance in VR, you tend to want to be able to see things right up next to your face, but also things that are really far away. And that's really a problem when you have large stations like this and you want to see everything as well as stuff that you're holding right up into your face. So when you have such a wide clipping range, what happens is that when you try to render things that are super far away, two planes that are close to each other, but like let's say you have one thing that's on top, you end up having kind of a fight. The rendering fights between whether it's supposed to render one or the other because the resolution's not big enough to keep track at such a distance what's on top of what. We can take a brief tour of the Blender file that I'm using to create the models that are then later imported into Godot. So here's without the star background. There's Mars in the distance, the chairs. There's a part of Debos that's still there. In reality, or in the simulation, you can't actually fly out this far. There's a window that you can't go through, so you can't actually see this sharp edge there. Anyway, so if you go back through these curvy tunnels, you see these more genetically engineered Lego trees to provide oxygen. Sure, that makes sense, doesn't it? I'm working on this, so eventually these will be actual trees with vegetation. I'm still working on an efficient way to both make the trees and import them. Not an easy thing to simulate and have decent performance, but there's going to be rivers and buildings and stuff like that. Up there is it's a Mars level, so in a station down at the bottom is going to be Earth gravity, but this level is going to be the Mars level, so you have Mars gravity there, restaurants, whatnot. In this game I'm slowly putting together, you'll be able to fly to the outside of Deimos and then land on one of these platforms and take a lift down into the interior of Deimos. So imagine coming in, landing your rocket on one of these platforms or your little ship there, get on a lift and take the train, board the train, go deep inside Deimos, and then end up back in the interior. So what's next on the to-do list? One thing is, for instance, this transfer vehicle, I'm calling it. So basically you have a rocket that comes up off the planet's surface or from some nearby asteroid or whatever. It flies into this transfer unit that passengers unload. Then once everyone is unloaded into the main cabin thing, the rocket goes up and is connected by tethers coming out of these spool things. Then it extends way out. Then it starts rotating, so that you have this dumbbell system again, tethered dumbbell. So the rotation will give it spin gravity, so people can live in this little pension type of thing down below. This is still a work in progress, so I'm still working out a whole bunch of things. In terms of reality, it's not necessarily the most practical design in the world, but in terms of video game playing, it's it'll be cool. You gotta trust me. There's some potted plants, you could say. You can tell they're genetically engineered for survival in space, obviously. Stairs just in case. More plants. Kitchen area. It's to do. And down below for the bridge and whatnot, other machinery, got to figure out how to maintain the equipment, make the air breathable and everything like that. And last but not least, this next rotational environment I want to talk about is a little bit different because it takes place on the surface of a planet, Mars in particular. On Mars, you only have like a third of a G compared to Earth, so 1/3 the gravity that Earth has. So if that turns out to be a problem, humans are going to want to have like more gravity. The only way to do that on the surface of Mars is to have a tilted track. I came across this paper by NASA from 2016 by Gregory Dorais. Not sure how to actually pronounce that. But he introduces a concept of a hypergravity vehicle that runs around on tracks, and the sides are tilted. It's a fairly detailed synopsis of how you can have a train spinning around on these tracks, or driving around these tracks, creating enough spin gravity so that you could still have 1G or whatever gravity you want in, and also be able to transport things to and from the stationary surface of Mars in these transfer vehicles. So I thought that was a pretty cool thing, and I wanted to see what that would actually look like if you were riding in one of these carts zooming around. So I put together this simulation where you're standing on a rotating track. You can touch the ground with your hands. Even though the ground is like right next to you, you're still standing up. So your apparent g-force is straight into the platform. You'd still get nausea after a while of riding around on this platform, I think. You're still going to want to have opaque windows and, block off enough of the view so you don't get everyone sick. But still, that's one way to have 1G on Mars. I need to flesh that simulation out a bit more. Right now, it's just a platform. It definitely needs furniture and chairs and whatnot. Something that takes into account that conical environment. So, thank you for coming on this tour of VR space stations. And here are some extra resources if you're curious about the subject. Thank you and good night.